Alright, cool. Looks like we're live. We've got like 2 more minutes before the stream starts. So, yeah. The lag doesn't seem too bad. I'm gonna check what the lag is. I think it's like under a minute. Just pretty usual. Yeah, this is the last stream, so. And I might do more, but it's unlikely. I suppose if the stream is a minute, then I can start like a minute early. Okay, yeah, so the lag is about 35 seconds, which means that I suppose it means I can start 35 seconds early, and there won't be an issue. Okay, yeah, make sure to subscribe, give this video a like, and yeah, okay, so I'm gonna get started. Okay, so the basic idea behind persistence, for the people who have never heard of persistence before, is that you should be able to revert to a previous state. So let's just say like a sample problem for persistence on an array. So yeah, the structure refers to persistence on an array, then segment tree, then Unionfind. Oh, is the volume bad? Can I edit that? Okay. Supposed to be a question mark, but whatever. I mean, the volume's the same as what it always is, so. I suppose I could speak a little louder. I'm not sure why the volume would be louder, but like, I'm trying to speak louder, and I guess I'll speak a little slower so it's more clear. Is this volume good? I hope it's good. Okay, that kind of sucks, but yeah, I don't know how to fix it, so sorry. Okay, anyway, so I'll speak a little slower and try to speak louder. So the idea behind persistence, yeah, this is so low you can tell me when the lag is over, I guess. So idea behind persistence, like a sample problem, would be, let's say you have an array with n elements, say n equals 7 here, right? And each element in the array, oh, cool. Not sure what happened, but that's good. Alright, so each element in the array, say, starts out at 0. And then you have queries. You have q queries. Q could be like 100,000 or something, and n is also 100,000. And for each query, the queries are given in order of time. You can have a query that says change, like a query could be a change array of, oh, I should, or let's put it set array of 5 to like say 4. So I'll just put like A and B, so this is general. Set array of A equal to B. Or it could be a question, what was array of A at time t? Right, so the first time you set the array of A equals, so like let's just say, let's call this query 1 and let's call this query of 2. So you could have a query 1, set array 1 to 4, 5. And then this, of course, is time t equals 1. And then the next query would be something like 1 set the array 3 to 4, and this would be at t equals 2. And then say 1 set 1 to 7, and this is at t equals 3. And then query what was, so this is like the query, and this is A, and this is B slash T. So what was array 1 at time 2, right? So then you have to, and of course this query is at time 4. Okay, so now you have to go back to here, and you have to figure out that array 1 was 5 at this time. You cannot use the 7 that's here. Okay, if you have a question about the problem I just described, please let me know. And I mean, yeah, I'm just gonna keep going because the lag's pretty bad. But like, just let me know, and I'll see it soon. Okay, so how do we solve this problem? Well, the idea is that each query, right? Each of these queries, you're only changing one element in the array. So okay, let's first look at the naive solution, right? The naive solution would be, okay, let's just say you have 3 elements. 1, 2, and 3. Right, so you start off with 0, 0, 0 at time t equals 0, and then at time t equals 1, you change 1 to 5, then at time t equals 2, it's kind of bad, but oh well. Time t equals 2, you change 3 to 4, and at time t equals 3, you change 1 to 7. Right, and then when you want to query for time 1, you simply access this array here. Now, of course, this is too much memory and runtime, because you cannot store q times n because q and n are 10 to the 5. This would be the naive brute force solution. Alright, so now the idea is that in each query we're only changing one element, right? We're only changing array A. So we only need to store the change, which is the change in one element, because the rest of the elements stay the same. Like for example here, right? This is the only one that's changed, this is the only one that's changed, then this is the only one that's changed. All the rest of them are the same as the previous, so we don't need to store the exact same element again. Okay, so to do this, we will of course use persistence. That's the topic of this video. So what we do is, for each element, we store, for each element, like for each index in the array, we store a vector. And this vector, oh sorry, there, look better. Okay, this vector stores, for every change that's made to that index, the vector will store the time the change was occurred, and it'll store the value that it changed to. So now our array will look something like this. Are you going to add HLD and persistent segment tree problem? So I'm not really going over how to solve any specific problems. I'm just going over the concepts in general. But I mean, sure, I could link up Codeforce's blog with a bunch of problems. Like you could just Google persistent seg tree problems, and which I did, and you come up with like a Codeforce's blog. So sure, I can just link those blogs and email them now, or add them in the description or something. So I'll do that, sure. Okay. So now, instead of this whole thing here, right? What we can do is we have the indexes 1, 2, and 3. And for each of these, we store a vector, which has a pair, which is the time and the value that it changes to. Now, since we're looping in order of the queries, it'll already be sorted by time because we're already looping in order of time. So the first query, so first of all, everything originally starts at 0 at time 0. So like this pair is going to be the time and then the value. Okay, so all the elements at time 0 are 0. Now we get the query of 1, 5. So this means that at time 1, this element is changed to 5. And again, the time comes from here, not from here. This is just the index. Okay, now the next query is 3, 4. This means that time 2, the value at index 3 is changed to 4. So time 2 is changed to 4. And I'll probably leave this dotted line here. Okay, the next query is 1, 7 at time 3. So we set at time 3, we set 1 to 7. And now we can binary search for the answer for the queries of type 2. So now the query says we want to know what 1 was at time 2. So we look at these values here and we binary search for the biggest value, for the biggest time that's less than or equal to 2. And the biggest time is 1. And so we can see here that at time 1, index 1 had a 5. So the answer is 5, which, oh, we're looking at time 2. This is perfectly accurate. Okay. Any questions about this? So I guess keep asking your questions, and like I'll see them when the lag's over, and I'm gonna move on to persistent segment trees. All right. So for persistent arrays, we were able to take advantage of the fact that only one element is changed. If only one element was changed, we could change just that one element, store the time that we change it on, and then binary search on the time. Right? So we can do a similar thing for persistent segment trees. Is volume too low? Okay, let me. Alright, give me a second. Let's see if I can do something about the volume. Okay, I'm glad it's fine for you. Yeah, the volume should be better now, hopefully. Okay. Anyways, moving on. Alright, so for arrays, we took advantage of the fact that since only one element in the array gets changed, we only have to store the change in that one element, and we store it at the time, right? And again, since we're looking at the queries in order of time, these values here are sorted by time, because we're going in order of time. Now for segment trees, we can do a similar thing. The reason the runtime of a segment tree is fast enough is because in a segment tree, only log n items are changed. Right? So segment tree will look something like this. Alright, so now if we try to change any one element, for example this element here, we change this element, and we change this, then we change this, then we change this. And since it's a segment tree, we know that the depth equals log n, right? Or is order of log n. Okay, glad the volume's better. You should note that like good is spelled with 2 O's. So, it's no big deal. I spell things wrong all the time. Okay, anyways. So we only have to change log n values in the segment tree. So we can apply the same concept that we did for the array. So for every node in the segment trees, we will just store the value that is changed to and the time. So alright, so every node is gonna be a vector instead of I'm not 9 years old. But if I was 9 years old, that'd be kind of cool that I'm a 9-year-old who knows persistence. But no, unfortunately, I'm not 9 years old. Thanks for deleting that. Okay, so right, so we have a vector that stores the time and the change. So here, basically, let's look at what the update code would look like. Actually, I think it's better if I just type the code and or faster. The code block takes like a while to get up, so I guess I'll just start writing it here. Okay, as normal, your update takes your index, your left, your right, and we're going to do this without lazy proposition. So this is going to be the value we want to, location we want to change, and the value we want to change it to. Okay, so of course we first check if we're out of range. And you can get the code to check specifically. This last week was, or I think 2 weeks ago. No, last week I did segment trees with in the heavy light decomposition. So you can get the code for that. If out of range, return. I'm not sure if this is big enough to see, so I'm just gonna. Actually, this might be big enough. Yeah, let me know if the text is big enough. Hope it is. Okay, got it bigger. So you have your index, your left, your right, your x, and the val. Obviously, if x is out of the range, we return. Okay. Now we check if L equals R, which means that x is in the range and this is the only one. If x is in the range and it's the only one, then we say tree index dot. Oh yeah, we also need to send in the time. T index dot push back, make pair. Actually, we could just do and place back, which basically is push down a pair, push back a pair. Persistent segment trees have arbitrarily large range. Yeah, persistent segment trees are just like any other segment trees. So you could have as large ranges as long as you're only updating. So normal segment trees can go for up to 10 to the power 9. You just have to do it implicitly, which means that actually, yeah, you could probably find research on that, but basically the idea means that you only create the children nodes if you're going into that value. So persistent segment trees and normal segment trees can go to the range 1 to 10 to the power 9. Just look up implicit segment trees and place back time and the value. Okay, and then we'll return. And then otherwise, let's say we're taking a max equals max. Okay, otherwise, we have to update left child, and then we update right child. Okay, then we take the max, and when we take the max, oh yeah, tree index dot and place back. So we have to add it to our vector. Oh, all good. All right, cool. Time, pair of time and so you want to take the max of the left child. Left child is tree index times 2, and then tree index times 2 dot size minus 1. So this means we're taking the last element. We're taking the last element in the in our left child dot second, because we don't care about the time, we care about the value. So this is our left child, and then we take the exact same thing for our right child. So we do +1 here and +1 here. We take the last element and we take the value, not the time. The time we set to our current time. Alright, so what this basically does, and I'm sorry I can't show the whole thing, but I'm just going to kind of scroll through it. Hopefully you can see it. Okay, so what this sort of does is, if we're on like a lower element like this one, it'll just change the value, and if we're on this element here, we'll add the max of this element here and the changed value, not the old value, the changed value. Okay, if you have any questions, of course, feel free to keep asking. But yeah, so I'm just gonna go on to the the query function because that seems important. Okay. Oh yeah, if you just joined in, be sure to subscribe, give this video a like, please. Thanks. Alright, cool. So for the query function, we have our index left to right. We have their query left and we have our query right. So we're trying to query this range at this particular time. And again, time is just an integer based on the queries. Like here, the first query is time 1, then time 2, 3, 4. Okay. So first, of course, if we're out of range, actually I'll just write the code for out of range. If query left less than r or left than or left is greater than query right. No, sorry. If query right is less than left, or right is less than query left, then this means that we're out of range. We return. We're taking the max, we return negative infinity. Because we're doing a max tree. Okay. If we are completely in the range, this means that now again we don't want to check if L and R is completely in the range of query left to query right. We want to we don't check if query left to query right is completely in the range of query R of L to R. We want to check if L to R is completely in the range of query left to query right. Query is complete in the range. Okay, if we're completely in the range, then we need a binary search. So binary search to get the right value. And just again, a recap like with the array thing, we're binary searching on these values here to figure out which one is the smallest one that is less than or equal to the time. And of course we have in 0, so it'll never be that there's no value that's not less than or equal to. Okay, so int a equals 0, because that's our smallest index, and b equals tree index dot size minus 1 because that's the largest index, while a is not equal to b. And again, you should know binary search. I'm going to write it just because persistence is complicated. If tree mid dot first, this first is a time. Yeah, this is true. It is log squared n. So maybe be careful with the constants, or hope that the time limit is a little higher. Okay, so if the time is less than or equal to the time that we want, then we can say a equals mid, else it's too high, so we do b equals mid minus 1. Since we're subtracting one here, we have to add one there. Okay, so then now mid is the index, the correct index, so we return tree index mid dot second, because you want to return the value. Alright, so this is how we do the binary search to get the persistence value. And if not, then we just return the max of the queries of our two of query left and query right. Okay, this is how persistent segment trees work. I don't think we'll be able to do Unionfind in 30 minutes, so I'm just gonna say it's gonna go over time, and I'm gonna explain how to do persistent Unionfind. Okay, so the idea behind Unionfind, and of course you have to know Unionfind to understand persistent Unionfind, but the idea behind Unionfind is that at every point in time, you like so for Unionfind, you store the parent of each node, and you store the size of each um, component, I guess you'd call it. Okay, now so there is like Unionfind has an optimization that like let's just say you're querying for the root of x. If you're querying for the root of x, right? So you say you get the root, and then you say parent of x equals root. And this is an optimization to make the runtime faster. It's easier to do persistence if you don't use this optimization, and you only change the root when you're combining elements. And the reason is because you have to store, because it'll be slightly faster because then you'll be storing less things. Alright, so you store two things, right? The parent of each node and the size of each component. Those two types of queries that it's related to DSU. Yeah, Unionfind is the same thing as DSU. Not DSU on trees, but it's the same thing as DSU. Okay, so there's two types of queries that you'll be doing. One is you'll be combining two nodes together, and two is you'll be checking if two nodes are in the same component at a particular time t. Okay, when we combine two nodes together, we first get to the root of each node, and then we change the parents and the size of only the root of the node. We don't change the rest of the elements. This means that we only have to change two values, right? So we can do the combine in log n, not log squared n like segment trees, because we only have to change the parent and the size. Now, if we want to change every single value, like as we're updating it, then that runtime gets a little tricky to calculate. But let's just say we're only changing the parent of the node and the size of each component. We have to change the runtime is log n because we're only changing O of one element. We're changing the parent of one node and we're changing the size of one component. And in fact, the size doesn't even have to be done within the persistence because we're not going back in time to combine things. So the only thing we need to keep track of, like with persistence, is the parent of each node. So we only need to really add one value. Sorry, the combine is, yeah, it's log in to find the parents, but it's O1 for the persistence. Oh, I think we'll be able to finish this by 9. I don't think I need to write the code for this, but I don't know, we'll see. Okay, now when I do query to see if two nodes are in the same component at a particular time t, we need to keep finding the parent at that time t, right? So now this becomes O log squared n because we could have log n parents, and for each parent we have to do a binary search to find the parent at that time t. Okay, I think I explained this well. Segment tree I definitely needed to code. Array I just sort of skimmed over because I was coding segment tree anyways. I don't know. I don't think I need to code this because segment tree is pretty much a similar code, but if I do, I will code this. And yeah. So finding the parent is log n. Oh no, finding the root is log n, sorry. Because you only know the parent of each node, and then that parent has another parent, and that parent has another parent. So there's log n, maximum of log n parents. There is an optimization to change it to O of 1, but that does not work well with persistence. If you want to suggest a problem link to me, I'll look at it. Technical world. In these two, there's an optimization to get the parent in O of 1. But not with persistence. So yeah, this is a thing, but this is true. The runtime's O of 1, which is better than log n. But it doesn't work well with persistence. So yeah. Okay. If there are no more questions, then then I'm just gonna end the stream. We didn't go that much over, just a minute or two. Which is not that bad. Just gonna wait because the lag might be a little longer, but I hope I answered your question. Cat93 if I. So lazy propagation gets a little tricky. Um, but yeah, it just still work because so for the lazy okay, in the lazy array, you would just store the same thing. You would store the time and the change, and then when you push it, you would push all the items. Like in your push function, you would push all the items from the lazy array onto the segment tree. So you'd push all the times, and yeah, I mean that should that's how you do lazy. Glad I answered your question. Yeah, lazy is kind of tricky, but so pretty much the exact same thing as the rest of the segment trees. Sort of like how Unionfind is kind of tricky, but it's really the exact same concept. Okay, be sure to give this video a like and subscribe, and yeah, I will possibly post another video, but this is the last one for uh this current set of videos. Alright, bye.